Hello again, class. This is Chapter 8.6, Angles and Polygons. The first part of the lesson will be to review the names of some of the common polygons that we have. A triangle has 3 sides. If the polygon has 4 sides, we call it a quadrilateral. A 5-sided polygon is referred to as a pentagon. A 6-sided one, perhaps you remember that one is a hexagon. We talked about this one last year, and this is the one that a lot of people don't necessarily work with a lot, so it's easy to forget the name, but it's a heptagon. An 8-sided figure, that's your stop sign. That's an octagon. 9-sided figure, which we did not work with last year very much, that is called a nonagon. A 10-sided figure, you probably remember that one. It's a decagon. And the 12-sided figure does have 2 names. Some people would call it a 12-gon, but it also is called a dodecagon. You will need to know that if I say a dodecagon, we're talking about a 12-sided figure. If you see a picture of a polygon, you count the number of sides. If you count that there's 7, then you tell me that it's a heptagon. The part of the lesson that is going to be a little bit more extended is to also deal with polygons and the sum of the angles of a polygon, which is why in part 2 we're going to talk about the fact that there are interior angles. For a polygon with n number of sides, so any number of sides, 3 on up, the sum of the measures of the interior angles is to take n minus 2 and then times 180. That particular formula is a very important formula to know. I would suggest you get a highlighter and you highlight this one. Now we're going to be dealing with it and working with that formula as we work through a couple of examples. Find the sum of the measures of the interior angles of each polygon. It really doesn't matter if you take 180 times n minus 2, the quantity n minus 2, or if you take the quantity n minus 2 times 180. Our book usually chooses to write it as n minus 2 and then times 180. In this particular case, we're going to count the number of sides. This is a pentagon, so it's 5. 5 minus 2 times 180, which is 3 times 180, which equals 540 degrees. So if we actually measured each of these angles, here, 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 and here, added them up, we would come up with 540 degrees. You can probably guess, you hopefully remember that if you're dealing with a quadrilateral, rectangles, for example, had 4 right angles, squares had 4 right angles, 4 times 90 is 360, but we can also use a formula. N minus 2 times 180 is going to equal 4 minus 2 times 180, which is 2 times 180, which equals 360 degrees. With the idea that, yes, if I drew a line here, a diagonal here, oh, look, I've actually divided it up into 2 triangles, and 2 triangles, each having 180, would be 360. If I kind of go backwards and go to this pentagon, I can draw a line here and a line here. You have 3 triangles. So 3 times the 180 equals 540. So you can do it by formula. You can also do it by drawing diagonals if you need to, from one vertex. You have to draw the diagonals from one vertex. Let's look at example 3. First of all, you need to identify that this is an octagon with 8 sides. Hopefully you counted, or some of you recognize it as a stop sign right away. So that's an octagon. We're going to take n minus 2 times 180. 8 minus 2 times 180 will be 6 times 180. And if you roll that through a calculator or do it mental math, you will have 1080 degrees in an octagon. A dodecagon, remember how many sides that has? Yes, it has 12. So we have n minus 2 times 180. 12 minus 2 times 180, which will equal 10 times 180. Don't need a calculator for that. That 0 goes on as a shortcut, so it's 1,800. When we talk about polygons, there are also such things as regular polygons, and every polygon that I've showed you so far happens to be a regular polygon. Although if you remember back to lesson 8.5, we talked about scalene triangles. If none of the sides are congruent, then that's not a regular polygon. So a scalene triangle is not a regular polygon. An equilateral triangle is a polygon. Now, if we're talking about a regular polygon, and this definition is one they expect you to remember, all the sides have to be congruent and all of the interior angles have to be congruent. So if you'll note for this hexagon, I have tick marked all the sides. I've also arced each of the interior angles. Now, you can find the measure of each angle of a regular polygon by dividing the sum of the angle measures by the number of angles. So let's move on to an example. In example A, find the measure of each angle of a regular hexagon. First of all, we roll it through the formula to find the sum of the measures of all the interior angles, using our formula n minus 2 times 180. So that's going to be 6 minus 2 times 180, which is 4 times 180, which equals 720. Now that's the sum of the interior angles. What we just talked about back here on the last page is that we have to divide that by the number of angles. Well, if we have a hexagon, if there's 6 sides, there's 6 angles. So we're going to take that 720, divide by 6, 120 degrees. Now, at this point, you please hit pause and you do example B of working with a regular polygon with 9 sides, otherwise known as a nonagon. Okay, here's the work that you should have shown, that the nonagon has the sum of the interior angles of 1,260. When you divide by 9, each of the interior angles will be 140 degrees for a regular nonagon. And that is the conclusion of lesson 8.6. Please reply with pineapples. Scouting out.